the synapse. Remember that synapse is just a very fancy way of saying where one neuron touches something else. In this picture here, you can see that the blue cell is synapsed with the purple cell. You can see that they're touching each other on all these little axon terminals. By the way, just so you know, your book also, for some reason, didn't used to say this, but now it does, calls them synaptic knobs. I don't know why. I will always call them synaptic terminals. But I want you to be aware that that's a possibility. If you hear synaptic knobs, it's the same thing as synaptic terminals. Anyway, it's a junction between two cells. The cell before that touch point is called the presynaptic cell. This is the one that's transmitting the signal toward that synapse, toward that connection. In this case, the presynaptic cell is going to be the blue cell. Now, the postsynaptic cell is the one receiving the signal. It's the one after that space. So the postsynaptic cell in this picture is going to be the purple cell. We actually have two different types of synapse. When we talked about the skeletal muscle, we actually discussed one type. The type we talked about is a chemical synapse. But we also have another type of synapse called an electrical synapse. Okay, electrical synapses are formed when two cells are joined by a special connection. So you can see that connection, that darker line between these cells here, okay? But they're joined and then they have the gap junctions basically hooking the cells together. Now remember, a gap junction, if this is the cell membrane of one cell and this is the cell membrane of another, basically make a pipe connecting the two cells together. So in an electrical synapse, you've got gap junctions that are tubular proteins called connexins that allow the ionic current to flow between the adjacent cells. Basically, what that means is, you know that sodium that we have flowing through the cell? If you think back to chapter 9, I had said the sodium goes through to the synaptic terminal and causes the voltage-gated calcium channels to open, right? Well, in this case, I don't need that to happen. Literally, sodium can just travel from the cell up here to the cell down here through this tube. Literally, like a pipe, it just goes through the pipe to get into the next cell. So an action potential in one cell generates an ionic current that causes an action potential in its neighbor. Basically, imagine the current being like a river that's flowing. If I put dye in a river upstream, that water will carry that dye downstream, right? Everybody's probably been to the Frio by now. So that sodium is traveling through the cell. Let me get another color because that doesn't look real good. The sodium is traveling through the cell, and then when it gets to this gap junction where they're being held together, zoom in please, it goes through these to basically flow right into this next cell here. It doesn't have to go through, and I have to release the neurotransmitter. The neurotransmitter travels across the synaptic cleft and binds to the ligand gated. None of that has to happen now, okay? So an action potential in one basically generates an action potential in the next. And pretty much it's like a flowing river. If one cell fires, the next cell fires because that sodium just flows into the next cell. We call it an electrical synapse because the sodium is going to be electrically charged. So we are literally talking about electrical signal, the sodium, traveling from one cell to the next. So we call it an electrical signal. Now, a chemical synapse. This is the one that you are used to. This is the same as what we saw in the muscle cell. We've got, again, horrible color, sorry. We've got an axon terminal right next to another cell's membrane. As the action potential comes down, which is sodium, it causes voltage-gated calcium channels to open. Calcium signals these synaptic vesicles to release their neurotransmitter, which travel across the synaptic cleft to get to these ligand-gated channels. When the ligand binds, the channels open. So we still have a presynaptic cell. This is our presynaptic cell because it's before where these two cells meet. The synaptic cleft is the space here. Okay, so we've got the space that's there. Then we've got the postsynaptic membrane, this second cell's membrane that is across from that space. Sorry. Now, neurotransmitter release. The action potential arriving at the presynaptic terminal causes the voltage-gated calcium channels to open. This is the same as what we saw when we were looking at the muscle cell. This process has not changed. Calcium comes in, signals my synaptic vesicles to release their acetylcholine. The acetylcholine, or neurotransmitter if you want just the generic term, travels across the cleft to the postsynaptic membrane where we have ligand-gated ion channels. In this case, ligand-gated sodium channels. Why? The ion going through it is going to be sodium. Now, it does kind of depend on which neurotransmitter is being released. It can be either excitatory or it can be inhibitory. So excitatory means I'm going to cause an action potential. I'm going to get the next cell to fire. Inhibitory means I'm going to shut that cell down. I don't want it to fire. It's pretty much exactly what the name sounds like. It's going to make something happen or it's going to stop something from happening. Excitatory, I'm going to make something happen. Inhibitory, I'm going to prevent something from happening. Now, the action potential. Again, one of my biggest pet peeves about how they write this is it's kind of like little snapshots. So again, you're going to have to put up with my crappy writing and drawing. Sorry. But you've got the presynaptic cell. Here's my synaptic cleft with the synapse where the two cells are meeting. Here's my postsynaptic cell. I've got my voltage-gated channels with my little ball and chain. If the charge inside of my cell is the same as the ball and chain, it's going to stay closed. If it changes, it'll open up. I've got my ligand-gated channel, my lock and key. If I've got a key that's not in place, it's closed. If the key is in place, it opens. Now, this is basically a drawing of what it would look like. If you look inside of this neuron, I don't know why it's not zooming in. Zoom in. There we go. If you look inside of the neuron, everything's color-coded. Potassium is orange, sodium is blue, calcium is purple, acetylcholine is pink, and the sodium-potassium pump is green. Look at all of the potassium inside of my neuron. Remember I told you, potassium is always highest inside the neuron. It's lower outside. Now, if you'll notice, the orange pluses are outside. It's just not near as much. So I have a lot of potassium inside, some outside. And by the same token, I've got a ton of sodium outside. And while I do have some inside of this cell, it's not much. Okay, I've got voltage-gated potassium channels, voltage-gated sodium channels with the ball and chain, and I've got my sodium-potassium pump. That's this green, I guess, clam-looking thing. I've got my voltage-gated calcium channels. They're purple. Acetylcholine is pink, and this is my ligand-gated sodium channel at the beginning of my cell. So we are going to start here, okay? We're going to start at the very beginning. How does an action potential start? So everything I'm saying is written in these places, okay? I'm not just pulling it out of my head, I promise. So sodium, the action potential, starts flowing down our synaptic cleft, right? And as it does, it causes these voltage-gated calcium channels to open. As they open, calcium floods into our synaptic terminal. That calcium signals these synaptic vesicles to release their acetylcholine, okay? So acetylcholine gets released, travels across my synaptic cleft, and binds to these ligand-gated channels. Okay, now remember, with ligand-gated channels, if I have the key in place, they open. Now, these are ligand-gated sodium channels. So what does that mean? Sodium's going to go through them. So when they open, sodium starts rushing into my cell. Now remember, sodium is like huge amounts of sodium are outside of my cell. So if I open a gate and it's going up downhill, right? If it's going downhill with its concentration gradients, it's going to come in. This is how we start an action potential in a neuron. This is the beginning of an action potential in a neuron. So here we are at the beginning where we had our ligand-gated sodium channels open, and you can see the sodium is starting to come in. Now remember what I said about it's on a current like a river. So even though it came in around here, it starts traveling down the cell. It starts moving down the cell. So the first thing it comes into contact with are these voltage-gated sodium channels. It causes them to open, and sodium starts flooding into my cell. Now it's still going to keep going. So sodium that came through the ligand-gated channels begins to change the charge inside the neuron. It becomes more positive. This change in charge causes voltage-gated sodium channels to open. As these open, even more sodium flows into the neuron, causing an even greater difference in charge. Now, if we're looking at this, excuse me, if we're looking at this with a probe and we're measuring what's inside the cell versus what's outside the cell, okay, you're going to see the inside become more positive. Just like this graph is showing over here on the right, it's becoming more positive. And what caused this? The voltage-gated channels started opening. Which ones? The voltage-gated sodium channels. This is depolarization. Okay, so depolarization is happening. The inside of my cell is becoming more positive. Sorry. Depolarization is happening in this section. Remember, we also said that they fire section by section like I'm knocking down dominoes. You'll notice that the next section has, again, a voltage-gated sodium channel, a voltage-gated potassium channel, and a set of sodium-potassium pumps. So this one is my first section that is firing. This is the one that I'm measuring, though, for this graph. So this first step, this first thing that's happening is depolarization. Now, again, remember that these are on a current, so they're still flowing down. Who's next in line here? Orange was potassium, so these are voltage-gated potassium channels. Again, I get enough positives in there and these are going to open up. Well, where is potassium highest? Let's go back to that original picture. Look at how much potassium is inside the cell here. Look at all of this. if we're talking about going from high concentration to low concentration, it's high in here, it's going to go out here because it's trying to get from high to low because we're just doing diffusion. So, dun, da, da, with this flowing down in that current, it's going to cause these potassium channels, these voltage-gated potassium channels to open. If I'm going from high to low, I'm going to start spilling that potassium outside of my cell because it's higher inside than it is outside. So as sodium continues to travel down the neuron, it causes the voltage-gated potassium channels to open. These potassium begins to flow out of the neuron, which causes the charge inside the cell to go down. So now we're here, and when potassium starts leaving, we start coming down like this. What caused the potassium to leave? The opening of the voltage-gated potassium channels. This is repolarization. Okay, remember I told you we're trying to rewind. We're trying to get back to resting membrane potential. The voltage-gated potassium channels actually open slightly more slowly than my voltage-gated sodium channels. That's one of the reasons why it allows that change in charge for sodium to come in and actually cause it to go real positive. Now, look at this section here. Look at this first section. Do you see how chueco that is? Do you see how messed up that is? I had tons of sodium inside, I have tons of potassium outside, and that's not the way it's supposed to originally be, right? So, who starts working? My sodium potassium pump does. This area here where I'm slightly negative, the after potential, which I can't fit in here. The after potential, this is where my sodium potassium pump goes, yeah, I gotta fix this. And it'll start pumping sodium out and potassium back in so that I can restore that balance that we saw in the original picture. So the first section of the neuron, the sodium potassium pump begins to use ATP to pump potassium into the cell and sodium out of the cell. This is refractory period. This thing is so messed up, it's not going to fire no matter what I do. Remember I talked about the toilet, and if the tank is empty, you're not going to get the toilet to flush because there's no water to flush it with. I have to get things back to where they're supposed to be and get balance restored before I can get even kind of an action potential. But the goal at this point is to get back to my resting membrane potential. I want to get back to that negative 70 that we started at. Meanwhile, if you, overshot. If you look at this second section up here, remember I told you that the sodium is like it's in a river and it's just flowing down. Well, as this sodium that's over here flows down, it's going to cause this next section of voltage-gated sodium channels to open. Sodium's going to flood in. It's going to keep going. The next section of voltage-gated potassium channels is then going to open. Potassium is going to flood out. The next group of sodium potassium pumps start working to fix this section. This is one of the reasons why we say it's like a line of dominoes. This first section here has to fire to get this next section to fire because of the influx and then flowing down of these sodium ions. Without that, none of this would work. So, in that section that we just went through, that first section, when I'm in after potential, this is the guy that's working. He's getting sodium back out, which you can see there. He's getting potassium back in, which you can see here. But again, it's going to take time to do this. Even if I move hundreds of sodium into the cell, I still have millions of sodium outside the cell. Even if I move hundreds of potassium outside of the cell, I still have hundreds of thousands of them inside the cell. So no matter what, at this point, I'm going uphill. I'm going against the concentration gradient. If I've got a car down here and I want to make it go up here, that's going to cost me energy. That's why we have this ATP here. Now, remember what I said before. We went through this step by step, showing each of the steps. There are 6 steps to this process, I'll say.